Our next speaker is Devin O'Kelly, and his mentor is Ralph Mason, and the title of his talk is Elasticity of Gas Challenge Response as an Indirect Measure of Vascular Quality.
Thank you, Dr. Linkinski. Thanks everyone for having me here today, and I'd like to extend a special thanks to Trey Campbell and Jenny Gerberick, who are some very talented technicians and our lab manager, and as well as my mentor, Dr. Ralph Mason, for giving me the opportunity to actually perform research. So the reason we want to look at vasculature in the first place is because it's the means by which nutrients and oxygen enter tumors, enter regular tissues, and that severely affects the energy distribution available within those tissues. Similarly, on an exit view, you can see waste and metastasizing tumor cells leave, and these properties, these delivery in and out, are determined very strongly by the structural characteristics of that vasculature. So in a similar way as to how you can travel very quickly on the Autobahn, but if you're driving in Dallas, you're not going anywhere, the quality of the vasculature has a very strong effect on how much oxygen will be delivered. This lack of oxygen has a number of clinical implications, not least of which is increased radioresistance. Hypoxic cells, which are chronically, acutely hypoxic, require as much as 3 times as much radiation to achieve the same kill rate as well-oxygenated cells, and that obviously has very strong clinical implication. Similarly, hypoxic cells tend to express very increased survival responses. This is just one example. They'll start secreting vascular growth factor. This causes a slow production of new vessels until such time as they reach normoxia. If this was a normal tissue, they would stop at that point, but being dysregulated, they generate a nasty tangle of poor quality blood vessels and continue to secrete over time. So in differentiating these two cases, there are a couple of salient qualitative differences that can be picked out in this image. The normal vasculature is kind of hierarchical, has good scaling properties. Each level of vessels resembles the last. In contrast, abnormal vasculature has very poor behavior. It's kind of drawn outside the lines. It doesn't follow the same rules as regular vasculature. And this dysregulation is something we'd like to be able to pick up on in a quantitative manner. So these are summed up in these two columns, but the main takeaway is that normal vasculature is conservative and well-regulated, whereas abnormal vasculature is dysregulated and generally wasteful with how it produces blood vessels. So in assessing these vascular beds, one will often perform an imaging task where you are examining some region of interest or some voxel. You'll introduce a tracer upstream of that voxel, and then you'll watch as the concentration of that tracer in that voxel changes over time. In this particular case, there's very clearly a sharp transition in contrast to a more slow transition here. This is due to the fact that they have their independent structures. So if we inject a tracer and follow along a single vessel, blocking off all others, we can see that as it follows this tortuous path, there is a slow increase of concentration of contrast agent in that voxel over time. And both of these take a rather winding path, and so it takes a rather long time for that to happen. Similarly, if we take a more direct path, we'll see a contrasting arrival time where there's a sharper transition at an earlier time. If we look at all vessels all at the same time and average over the entire ROI, we'll see the sharp transition in the normal vasculature because the path lengths are all about the same. And in this winding tumor bed, we will see a very large distribution of those travel times, and so they'll have this much more spread out transition. The way we want to look at this is to say, now we have this forward model, can we invert that and get that information back out? The way we do this is by using a new imaging method called multispectral optoacoustic tomography. We have this on South Campus, and we've gotten pretty good at using it. It's effectively laser-driven ultrasound, and so that leads to the setup of a mouse and a holder in a plastic wrap sort of situation, through which it is breathing oxygen and anesthesia through that nose cone. It is suspended in a water bath, which has these laser sources. Those shine light upon the mouse. That causes generation of ultrasound waves, which we can then detect to form an image. We can tune the wavelength that we use, which allows us to detect the oxygenation state as well as rough concentration of hemoglobin. And we can get these images at a fairly high time resolution of about 1 second in an ideal case. There we go. So we want to assess this experimentally in a more non-invasive way, rather than injecting a tracer and adding to our difficulties of having a mouse in a water bath. So a variety of modalities are actually sensitive to changes in oxygenation, and this is a good thing because it allows us to use oxygen as a perfect tracer. What I mean by that is that the addition of oxygen does not actually change the blood volume in any significant way, except through change in hemodynamics. And so if we are observing through our voxel over time, and we are imaging on air and switch to oxygen and then back to air, and we calculate the oxygen saturation over time, we will see this rising exponential curve that then decreases once again. This resembles a materials test known as a creep test, and that similarity goes all the way down to the basic math of it. So if we have a capillary bed that's at some baseline oxygenation and a elastic material that's at some baseline stretch due to its inherent weight, if we add weights to our elastic material, if we add oxygen to our capillary bed, we will see a change in length of our elastic material, and we'll similarly see a change in concentration in our vascular bed. The summary statistic for this stretching is known as the elasticity. These are the only equations here. And so it just relates the applied force to the percent change of the length. Similarly here, we're changing the percent of oxygen in the inhale gas, and looking at the percent change in oxygen saturation. This has a number of good mathematical properties that I'm not going to go into, but this seems to be a fairly ideal way to summarize this sort of experimental data. So we actually wanted to test this out in a real situation. So we have here an MSOT image, which is a cross-section through a single wavelength through a female nude mouse which has an implanted lower memory fat pad breast tumor. We processed this data with some in-house developed software, so I can go into that afterwards if you'd like to talk about that. I'm going to be pointing out a couple of ROIs in the coming slides. So here's the spine, here's the abdominal aorta bifurcating down to the femoral arteries. Feeding vessel here feeding this large tumor ROI. And so from single wavelength image, it's not apparently clear what is going on inside of this, but we can generate total hemoglobin and total oxygen maps, which, although a bit messy, we'll just look at the ROIs. So for total hemoglobin, it is unclear that there is a very substantial change. There might be a little bit of change in the center of the tumor ROI, but it's not very outstandingly clear. In contrast with the SO2, there is very substantial change, but quantifying that is perhaps a bit of a challenge. If we calculate the elasticity, that is the percent change in total hemoglobin, or the percent change in SO2 in relation to the change in oxygen gas, we get these images. Black at 0, cool colors are negative response, warm colors, positive response, and black at 0. We can see that there is a huge amount of intratumoral heterogeneity, which is obviously very characteristic of a wide variety of cancers. But we also see that there are some very well-responding focal points in the center of this tumor. Similarly, it is not immediately clear that there is a pattern here, but it is substantially different from the SO2 map. So we wanted to assess this and see whether or not this dynamic assessment could be applied to tracking treatment response. And so the challenge was repeated 3 times at 0, 3, and 24 hours. Immediately following the 0-hour test, we administered a vascular disrupting agent, which is intended to shut down poor quality vasculature, dysregulated vasculature, and therefore make it more normal or a bit more like the spine, for example. And so here we can clearly see that there is a strongly responding area where the feeding vessel was, the spine and abdominal aorta are responding in a normal fashion, and the tumor overall is showing a diversity of response. After 3 hours, this is normalized to resemble more of the spine and abdominal aorta, and by 24 hours, we see retained shutdown of the feeding vessel, but a general catastrophe throughout the rest of the tumor. We can perform histogram analysis on this, similarly to DCE MRI, and that tells kind of an interesting story. So we have this initial distribution throughout the tumor volume, which is symmetric, seems to be Gaussian. At 3 hours, we see this substantially changed distribution, and this very strongly resembles normal tissue. At 24 hours, after things have had a time to recover and be affected by the drug, we see a rough return to the same distribution as hours, but with a fattened left tail. And so there is very clearly a large amount of diagnostic value to this metric, but we are still in the process of going through the theory and making sure that everything works well, and hopefully we'll be able to translate it to other modalities such as DC MRI, oxygen-enhanced MRI, and the like. So with that, I'd like to thank everyone in the lab and all our collaborators, funding bodies, and I would be happy to take any questions.
Anybody have any questions? There's a question in the back. Yvonne.
Do you have any correlation with CD34 vascularity in tissue?
We do have some histology that we have not had a chance to look at yet, but that is one thing that we're definitely going to use as a V&V correlate.
So in MSK, the extremity sarcomas are very big. You know, they are anywhere from 5 to 15 centimeters stationary tumor sitting there where this ultrasound can be applied. Where do you see the translation? You'll have to give oxygen and all that to look at it, or you could do it without?
Could you repeat the question, please?
Could you do without giving oxygen in a human patient in vivo?
The reason we wanted to use the oxygen as a tracer is because it allows for a switching off of the oxygen. So whereas with regular tracers, you have one shot, you have to wait for it to clear out from the vasculature entirely. With oxygen, it clears itself out, and so that gives you the opportunity to do more creative oxygen challenges than just simply giving repeated boluses of tracer.
So where do you see the translation? Like, do you think it'll be translatable in few years in humans?
I think that is a very good question, and I would hope so, but it's rather difficult to say right now. I think the fact that it's non-invasive and pretty easily translatable and allows for very strong patient compliance is a plus for that, at least.
I have a question. Thank you for the presentation. In addition to oxygen being a tracer, oxygen may have some impact on the permeability and dynamics of the vascular bed. How does your model compensate for that?
That is actually a difficulty which is a bit more challenging to address, but we're looking into how we are going to deal with that, but it's hard to say for the time being.
Thank you.
Thank you.